Hi, welcome to our discussion today of acceleration of falling objects. Today we're going to be talking about the changes in velocity and distance for falling objects, as well as taking a quick look at how vertically thrown objects are pretty much the same thing as a falling object. Let's get started. So free fall is a very specific idea in physics. It says when an object is falling only due to the force of gravity, that's free fall. So basically, no air resistance. Now on Earth, obviously there's going to always be some air resistance, but for heavy objects traveling at relatively slow speeds, that resistance will be small and we can neglect it. So today we'll look at just free fall. And acceleration on Earth due to free fall is negative 9.81 meters per second every second. So something loses or changes its velocity by 9.81 meters per second every second, and it does so in the negative direction. What that means, if we have a number line here, and this is the positive numbers, and these are of course negative numbers, the negative direction is anything toward the negative in the direction of the negative side. That's a negative change, and this is a positive change. It's moving in this direction. So you can see a negative change if you are moving forward, you're slowing down and then speeding up backwards. And a positive change means that you are either slowing down backwards or speeding up forward. Your velocity is going in this direction. All right. Now, that's a tricky number to work with for calculations. So what we like to do in physics, we round this off when we're talking about example problems, and we round it off to a negative 10 meters per second. Now, just to ground you in some units you might be more familiar with about how much of an acceleration this is, that's about negative 22 miles per hour per second. And you'll remember, like, a really fast sports car can get upwards of like 0 to 60 in 3 seconds. That's at 20 miles per hour per second, and this is even faster. So if you have a crummy car and you're like, I really want it to be a good car and accelerate fast, one thing you could do is drive it off a cliff, and it'll start instantly accelerating at negative 22 miles per hour per second. You'll actually out-accelerate a Porsche. Now, obviously, there's some drawbacks to that technique, but it would get you a good acceleration, to say, for sure. So when we're working with problems, we'll be using this rounded off number. When we're working with real stuff in the lab, we need to be using this exact number of the acceleration of gravity, just to keep in mind. Now, as we take a look at the free fall, there are two equations that are going to really help us. First of all, we know that the acceleration is equal to the change in velocity divided by the change in time. Now, since we're looking at velocity and distances here, I'm going to solve this equation for delta v. And to do that, we're going to multiply both sides by delta t, so change in time. And we get here, these two cancel. We get here that the change in velocity is equal to the acceleration times the change in time. Now, the acceleration due to gravity on Earth has a special letter for it called g. And that's equal to that negative 9.81 meters per second. And this is simply the acceleration of gravity. And of course we know that we're going to use the approximate number of negative 10 meters per second. So I'm going to change this last here, just the change in velocity is equal to the acceleration of gravity, g delta t. And then the other one we need is a distance equation, and this one I'm just going to give to you. The change in distance is 1/2 acceleration times the change in time squared. Now again here, a is equal to g for falling things, so delta d is 1/2 g times delta t squared. Now this little squared thing is really important. We'll talk about what it does to the distance in just a minute. Let's take a look now at what happens when we drop an object. Let's look at what happens to its velocity and the distance it changes. So let's put our person up here on the top of this really tall cliff, and they have a ball in their hands, and at time 0 they drop the ball. So at time 0, of course, their velocity of the ball is 0. The change in distance, it hasn't moved yet, is also 0. And our ball is now going to fall down due to gravity. Let's look at its velocity first. We're going to remind ourselves that the acceleration is g here, which is negative 10 meters per second every second. So after 1 second of falling, it's going to go negative, its velocity is going to change by negative 10 meters per second. So here it's going to be at negative 10 meters per second. Now remember, that doesn't mean it's a bad thing. Negatives aren't bad here. They just mean that the velocity is a downward instead of an upward velocity. So our ball is speeding up downward. Now the next second, it's going to speed up by the same amount. It does this every single second. So we're looking at negative 20 meters per second, negative 30 meters per second, negative 40 meters per second. Every second, it speeds up by 10 more meters per second in the downward direction. So far, so good. Now the change in distance is a little more complicated. The change in distance here is equal to 1/2 g, which is that negative 10 meters per second squared, times delta t squared. So when we do this out for this delta t, we have to say our change in distance is equal to 1/2 times negative 10 meters per second times t squared, in this case 1 second squared. Notice a few things here. The seconds squared are going to cancel with these 2 seconds. The 1 gets squared still, I'll put that there. And then the half turns the 10 into 5. So in the end, we're going to have negative 5 meters, because that's all that's left here, times whatever our time is squared, in this case 1. So we get negative 5 meters. So we've lost 5 meters of height. So our change in distance here is just like before. So this is going to still be, a negative 5 meters per second times 2 seconds squared. Seconds are going to cancel with seconds. 2 squared is 4 times 5 is negative 20. So we've lost 20 meters from our starting point. So we're 20 meters below it. So our change in distance here is negative 5. And we know those seconds are going to cancel. I'm going to cancel them right away. Times, and then 3 squared. 3 squared is 9 times this is negative 45. And we continue this process, filling in all of them. 4 squared is 16 times 9 is 80. Or sorry, times 5 is 80 meters. Negative. And delta d is negative 5 meters times 5 squared, which is negative 125. And if you do the same math, you get negative 180 meters. So this is how much we've lost distance by. So let's fill in where our ball is. So at 0 seconds, it's right there. At 1 second, it's 5 meters below. It's lost 5 meters, so it's right there at 1 second. 5 meters. Now, at 2 seconds, it's lost 20 meters. So you'll notice it's actually gotten farther away. And that's negative 20 meters at 2 seconds. And then at 3 seconds, it's at negative 45, which is down here somewhere. And that's 3 seconds and negative 45 meters. And at 4 seconds, I'm going to run out of room here. It's gotten even farther away, which means it's 80 meters away. And then 125, it's here. And then 180 is way down here. And you can see that every second, the distance gets bigger and bigger and bigger. And that's because every second, of course, we're moving faster and faster and faster. And that's where that squared comes in. That squared is what makes that distance grow really fast. Okay. So that's free fall of a dropped object. And any object does this as long as there's no wind resistance or air resistance. It's free falling. Just gravity causes this to happen. So now we're going to take a look at what happens when we throw an object vertically. So this object's been thrown at 30 meters per second upwards. And we're going to look at how its velocity and distance changes. To start with, we've got to establish where it goes without any change. So without any acceleration because of gravity, if we threw it at 30 meters per second, it would start here at 0 seconds, and it would be 30 meters away after 1 second, and then 60 meters, traveling at a constant velocity, 90, and then 120, and then about here for 150, and maybe up here for 180. And that's the 1 second, 2 second, 3 second marks. Of course, without any kind of force of gravity, it's traveling at a constant speed of 30 meters per second and reaches a maximum height of 180 meters. This one's 150. Maybe start from the bottom. 30 meters, 60 meters, 90 meters, 120 meters. So this is without gravity. I'm going to write it up here, without gravity. Because remember, these numbers tell us our change in velocity, our change in distance, as if from where they would normally be without gravity. So this is where it would normally be without gravity. It would have flown upwards, it would have kept its constant 30 meters per second, and it would have had those different heights. So of course, with gravity, let's take a look at what's happening. So our actual velocity, we start out at 30 meters per second. And I'll switch over colors here. 30 meters per second. And then a second later, we're going to lose 10 meters per second because we have a negative acceleration here. So we're going to be only going at 20 meters per second. And then after 2 seconds, we're going to have lost 20 meters per second from our original 30, which puts us at only 10 meters per second. Because remember, if we didn't accelerate, we'd be going 30 the entire time. That means that this one is 20 less than what we'd normally be. Now on this one, we'd be 30 less than 30 meters per second. And that means we'd be at 0 meters per second. And then 40 less would be negative 10, negative 20, negative 30. Notice for velocity, the same pattern happens. We're going in the negative velocity direction. So we're moving towards negative velocities. We're decreasing our velocity by 10 and then increasing in the negative direction. Now the height's where it gets a little more strange. We know the change in distance of our heights, and these should all be negative, are all negative, and these are the numbers we got to before on the previous slide. Now let's look at where our actual heights would be. So after 0 time, we'd still be at 0 height because it still got tossed up. And we're going to take a look at the blue ones over here with gravity. So this one's still at 0. Now here, it's lost 5 meters. It's 5 meters away from where it normally would be. It would normally be at 30 meters, so at 1 second it's 5 meters away from that. It's 25 meters less. Oh, sorry, 5 meters less for a total of a height of 25 meters. So instead of being 30, it's only 25 because the acceleration has caused a loss of 5 meters. So we'll put that number right there. Now at 2 seconds, the acceleration has caused a loss of 20 meters, just like a fallen object. So here at 60, it's really not at 60, it's lost 20 of those meters, which means it's down here somewhere at 40 meters. 40 meters. Now here at 3 seconds, it's lost 45 meters. So we go up here to 90, it would normally be here, it's lost 45 of those meters, so really it's down here at 45. So it's only at 45 meters now. Now here at time 4, we're losing 80 meters of where we'd normally be. Well, at time 4 seconds, we'd normally be at 120. If we lose 80 meters of that because of acceleration, we're actually down here at 40 again, which is strange. I mean, now we've hit our top and we're headed back down. And notice we hit our top of 45 meters at the same time we hit our velocity of 0 meters per second. That's an important thing to notice. And then, so this brings us back down to 40 meters. And this will be losing 125 from 150. So we're not there. We've lost 125 meters. That puts us down to 25 meters again. And then at 6 seconds, we would normally be at 180 meters, but we've lost a full 180 meters. That puts us back here down at 0. At 0 meters per second.